mission that hasn't flown yet. I'll just wait for my slides to come up. So I'm going to give an overview about the LADEE mission, the Lunar Atmosphere and Dust Environment Explorer mission that's being developed here at Ames and with our partners at Goddard. And assuming that my slides do show up, I have to give one caveat. Those of you who are paying attention will note in the footer of my slides the word LEAG 2011. This is indeed the same set of slides I gave last year. And don't worry, I did actually take the time out to make slides for you today, but my computer refused to give them up. I woke up to a dead hard drive. So don't be offended. And if I say something that's different from a slide, it's because there's been updates since then. Worse yet, if I start talking to a slide that doesn't exist, just please bear with me. And how do I advance? Where do I point? Okay. All right, very good. Thank you. So what is LADEE? LADEE is going to study the lunar exosphere and dust environment. These are a host of very interesting science questions that were sort of left open-ended after the Apollo mission. And we've gained some progress since then with remote observations in LRO, but LADEE was specifically designed to study this particular problem. So characterizing the tenuous lunar atmosphere is goal one, and looking at lunar dust as a potential component of that atmosphere. We're doing a few other things. We're doing a technology demonstration, which is testing a laser communication system, which would enable very high data rate communications from the moon. And it's also demonstrating a low-cost lunar mission. We're using a modular spacecraft design, a new way to get to the moon on a Minotaur rocket. And right now we're scheduled to be launched mid-next year, and I'll give more details on that as we go ahead. So let me give this a try. Okay, it worked. So let's talk about exospheres. An exosphere is a very tenuous atmosphere. Most planets have one. It's so tenuous, in fact, that they are collisionless, which means that all the neutrals are existing there without seeing each other. And probably most of you are used to an exosphere that has a dense atmosphere as its lower boundary. But in the case of small, relatively airless bodies like the moon, the lower boundary is a solid surface. And what that does is that gives the lunar exosphere a completely different set of dynamics and behavior. So who cares? Well, you take a look at all the small airless bodies in the solar system, and it's quite probable that a surface boundary exosphere, an exosphere whose lower surface is solid, could be the most common type of atmosphere in the solar system, and we know very little about them. Because this atmosphere, this exosphere, is derived from the surface, they also have the potential to tell us unique things about the parent body. And so the moon is an excellent place to start to characterize the exospheres of airless bodies in general. It's nearby, it's easy to get to, we have lunar samples, we know what it's made of. So we have constraints on the composition and the behavior of that lower boundary. We have a flotilla, as you've seen, of spacecraft currently in orbit around the moon that are providing all kinds of information that are going to be useful to LADEE, helping to address this problem. Lots going on at Mercury as well. We're learning all kinds of things from MESSENGER about an exosphere about that planet. And you can extrapolate what we learn nearby to all kinds of small bodies, Europa and other icy moon satellites, large asteroids and KBOs perhaps. There's also this component of dust that everyone's been curious about. And there's some evidence on small bodies, for example, like Eros, that there may be dust motion happening, perhaps generated by plasma effects and charging, electrostatic effects. There may be some evidence for that at the moon. Maybe not. We'll have to see what LADEE reveals, but that is another goal of LADEE, is to understand how dust is tied into the exosphere environment and what causes its variability as well. If you saw Jasper Halleck's talk on Artemis, you've seen this picture before. This is a space physicist's picture of the moon, and you can see there's a lot going on. This tries to outline all the processes relevant to exosphere generation and variability, and perhaps dust variability as well. The moon is bombarded by all kinds of things. Solar wind plasma, energetic particles, solar storms. The moon comes in and out of the influence of the Earth's magnetosphere as well. That's another change in plasma environment. And one exospheric source is ion sputtering. Sputtering by ions producing a neutral. That could be an important variable source. You also have other sources as well. Micrometeorite impacts, the vapor clouds from those can produce a component to the exosphere. The moon itself may be a source from internal activity. And there are also thermal effects. If you have noble gases lying around, they can condense and then be liberated in the diurnal cycle of the moon's rotation, depending upon how and when they condense. So there's a whole plethora of sources here that could cause exospheric variability. And the goal of LADEE is to unravel the physics behind all those processes. As we also heard from the Artemis talk, there is also charging happening on the lunar surface. And this is caused by photoemission, plasma, ions, and electrons as the moon goes through the variable plasma environment. And we're learning a lot of new things about that just this past year. By and large, the central message is that changes in the plasma and illumination environment cause changes in the surface potential of the moon, and that has the potential to generate electrostatically lofted dust. Over what scale and what importance that generation has is one of the questions that LADEE is going to try and answer. This also highlights the incredible synergy between LADEE and Artemis. Artemis is going to provide some excellent constraints on the plasma inputs that we can correlate to what LADEE measures. Okay, next slide, please. So let's talk a little bit about the lunar atmosphere. Here's an example of what we've learned since Apollo. This is ground-based imaging of the sodium atmosphere. It's easy to see because sodium is really good at resonant scattering of sunlight, and so it has this kind of fluorescence which you can detect remotely. And so we have a lot of information on things like sodium and its cousin potassium that gives us some idea about exospheric behavior. One can look at the scale heights and densities as the moon goes through different environments. I think to this day it's still debated whether or not micrometeorite impacts, solar wind, or magnetosphere are the most important drivers for the source of the variability of the sodium exosphere. We also know from Apollo, but not shown here, that there's argon, for example. That's a good example of a thermally devolved and condensed species. In fact, if you were sitting at the lunar terminator and came into sunlight, you would experience a literal argon wind coming by you, and that's because the argon is heating up from the surface, coming off. It goes at some low scale height of 10 to 20 kilometers, then condenses back down on the cold side. And that's a thermally driven one. So those are two examples of very different processes. You can think of an exosphere almost as a combination of maybe 50 or 75 different kinds of atmospheres, because each species doesn't know that the other species is there, and they all respond to different inputs. Next slide, please. I wanted to have a few words about lunar volatiles, because this is a really exciting and recent development, particularly with the M3 and other observations of this thin veneer of hydroxyl and water on the surface of the moon, as well as the incredible discovery that LCROSS made of substantial volatile deposits in the polar region. There's several different ideas about how volatiles are generated and evolved in the moon. One idea is that they're relatively primordial. Perhaps they were deposited there long ago, and for some reason that we're still trying to figure out, the volatiles have been stable over long periods of time. There could also be active processes in which volatiles are being manufactured and cycled on the moon, almost a lunar water cycle, if you will. And one of the sources for that could be the solar wind. And if you take a look at some of the remote sensing observations from M-cubed and BIMS and epoxy, there's a hint in some observations of a diurnal variation in some of the hydroxyl and or water content. And that hints at the possibility that there is an active exchange process between volatiles or volatile precursors and the exosphere. And if that's true, that's a question that LADEE will help resolve. That is, that process is happening in the exosphere, and LADEE is going to be exceptionally good at measuring OH in particular. And there aren't too many processes that could produce OH, we don't think, that don't involve water. So that's going to be done with remote sensing, so we can get down very close to the surface with that measurement. And so this is an example of how an exosphere and studies of the exosphere could be important in understanding fundamental things about the moon. And so the observations we make could bear on the volatile question. Next slide. Okay, let's talk a little bit about dust. We saw some really great images of Tycho, I believe, earlier in LRO, and this is from Surveyor 7, I believe near the Tycho rim, and it's looking at sunset. And of course, the thing to pay attention to is this glow on the horizon, later termed lunar horizon glow. Similar effects seen by orbit, but a different morphology. This is far too dense to be anything other than a high concentration of dust, 5 to 10 microns in size, much more highly concentrated than one would expect from, for example, secondary ejecta from an impact. One leading theory is that this is electrostatically levitated dust. And it's also occurring at the right time near the terminator when we might expect a large change in the surface potential of the moon. So this is certainly intriguing. It hints at a dust transport process. Who knows how important it is, whether it's a global phenomenon or perhaps only a local one. That would certainly support similar theories about what happens on smaller bodies like Eros. Next slide, please. A little more controversial is the existence of a high altitude component. And from Apollo, we had eyewitness accounts, and we also had coronal photography that hinted at the possibility that there was some type of particulate material near the terminator regions. And if it was dust, it was very small, submicron, and had a pretty severe scale height of only a few kilometers, and low densities, for example, 10 to the minus fourth per cubic centimeter at 50 kilometers. So not a big component, but a potentially measurable one. And this graph shows kind of a summary of all that work, looking back at Apollo and giving it a kind of a second revision by Dave Glenner in 2011, where you see the distance from the terminator here and the height in kilometers, and then the blue to black is basically a density of dust. And by the time we get to LADEE altitudes, we're looking at 10 to the minus 3, 10 to the minus 4 per cubic centimeter, which is a pretty low density, but if it is there, that's more than can be explained by many processes. And electrostatic levitation is one leading candidate. So hopefully LADEE will help settle this question. Next slide, please. This is a schematic of the LADEE spacecraft, the most recent one, and probably very representative of what's going to fly. And I'll show actual photos of the instruments in the next slide so we can actually get away from computer-aided design. But sticking with the spacecraft for a minute, you can see this is the bus, and it's a modular design. It's stackable, made out of segments. It's composite for lightweight and strength. The instruments are mounted in a combination of body-mounted positions and on a top radiator deck. And there are 4 main instruments, one of which is a technology demo, and I already talked about that. That's the Lunar Laser Comm. And I'm sure everyone here, particularly camera people, are looking forward to 600 megabit per second data rates from the moon. That's going to be a great thing. So hopefully that'll work and become something that we can use in the future. We have a neutral mass spectrometer, and that's literally going to scoop up the exosphere, neutral particles, and determine their composition. We have the lunar dust experiment. That's going to measure this very tenuous, potentially tenuous component of lunar dust at high altitudes. And we have an ultraviolet and visible spectrometer, which is going to do remote sensing of both dust and the exosphere. Next slide, please. Okay. So these are the instruments. They're about ready for delivery. LADEE is getting towards the end of phase C, so most of them are calibrated and waiting to go. We had a lot of progress on that since giving this last talk. Next slide, please. This is the way we're getting to the moon. This is the Minotaur V launch vehicle. It's a derivative of a successful series of earlier Minotaurs, 1 and 2 and 4, which have launched many payloads into space successfully. LADEE has the addition of an extra Star 37 motor that'll help get it to the moon. You can think of it as a gigantic solid rocket getting us into space. And if this is successful, it'll be another low-cost option for our lunar missions. Next slide. So this is an overall view of the mission, where we get put into a high-altitude phasing loops. That's part of the orbit design, and that helps broaden our launch window and get us to the moon at the right time. Then we do a standard lunar transfer, and we go into a checkout phase, which is a 250-kilometer circular. We then bring that down to a 250-kilometer elliptical as we go through a 30 to 40-day checkout, and then finally into the final science phase, which is a low-altitude elliptical, which can go as low as 20 kilometers and as high as 75 to 90 when we go into our prime science phase for a 100-day mission. And again, we'll be looking at exosphere variability and also the dust question. Right now, the launch is scheduled for August of 2013, so hopefully within a month after the next Lunar Science Forum, we will be flying to the moon with LADEE. And I'll end my talk there and take any questions. Thank you.
Okay, any questions? There's one. Mark Robinson.
Any depth that's, it's very fine, but it's at the altitude of LADEE. Would that all be lost to solar wind pressure, or would it actually go back to the surface?
Yes, that's actually a good question. And you can sit down and do a quick back-of-the-envelope calculation about the V cross V force that would carry away a particle of a certain mass. And you have to get below 1/10 of a micron, somewhere between 50 nanometers, maybe even 20 nanometers, and that'll get lost. And there's actually some evidence that that's going on in other places in the solar system, and it could happen at the moon. So a component of that could be lost, but if they're 1/10 of a micron, which is the most likely size distribution that we think we know from Apollo coronal photography, those probably would not be lost. So a lot of that would come back down.
Does the Apollo 17 dust detector data give you any data on the size frequency distribution of that material?
Are you referring to LEAM? Yeah. So the LEAM results tell that the best message I get from LEAM is that the activity is concentrated near the terminator. There is a lot of debate about what LEAM is actually telling us. Some people are not sure that it's actually a dust signature. There's a lot of debate. So I don't think we're at a point now where we can really get a size distribution out of that. The main value has been temporal correlation with conditions that we think might cause dust motion.
Okay, let's thank Greg for this wonderful talk and move